All right, so we're going to do a panel. So I want to invite Dr. Dirksen. All right, all right. Is Dr. Bonneman coming up? And Dr. Susan Hamilton? I saw Dr. Bonneman in the corner. He's here. Yeah, could you go grab him? Don't be shy. He's right there. Okay. All right. There he is. All right, welcome. So I think this group is already aware and knows Dr. Bonham and Dr. Dirksen have spoken. I want to introduce Dr. Susan Hamilton. She is chair of integrative physiology at Baylor College of Medicine. She has over 30 years of research on excitation, contraction, coupling, and RYR1 related diseases. She focuses on new treatment targets and developing mouse models to test therapies. So again, this is another all-star crew up here. You're not going to find more brain power than what we have right here. I'm embarrassed to be on the same stage, to be honest. So lots of issues have come up over the last couple sessions on DNA-related issues, gene therapy, gene editing. I know all of you come at this with a slightly different perspective. I think I want to start with kind of maybe the news of the day related to, we've talked a little bit about the issues related to liver toxicity and the need to give a high dose of virus to get the efficacy that one needs in muscle. Dr. Bonneman, I think you kind of are probably closest to this. Can you comment on what's happened in these recent trials briefly, and then comment on kind of what that means and kind of at the liver level, but also kind of moving what the implications are for the field of gene therapy, as specifically muscle gene therapy? Jared, can we get some more microphones? Oh, here, Lena's coming. Come on, Lena. How about a hand for Lena? No RYR1 issues with Lena, just to be clear. She's running fast. All right, Dr. Bonneman.
Yeah, so the liver toxicity in AAV gene therapy actually has a long history. It really started with the very first gene therapy trials for a bleeding disorder, hemophilia, where the gene therapy was given to the liver with the idea that the liver would then make the clotting factor that was missing. And then it turned out that in some patients in these early trials, there was a liver inflammation that came up a few weeks later. And that, of course, had the effect that the liver cells that were supposed to make the clotting factor were taken out by the liver inflammation, and the entire effect of the gene therapy went away. But what people learned at the time is that this is driven by the immune system recognizing the virus capsid. I missed the last two sections, but you talked about AAV and capsid and all that.
Yep.
Okay. So the AAV, of course, on the inside has the therapeutic gene, but on the outside it looks just like a virus. So it has the capsid, and the immune system can take notice and then recognize, in particular, when the virus has never been seen, which is, of course, the idea in gene therapy. You give it to people who have never seen the virus so that it doesn't get rejected first off. But once it's in the system and presented to the immune system wakes up to the virus, makes antibodies, but also T cells, which are little immune cells that come in a version that is created to destroy foreign exposing cells. And so those are cytotoxic T cells. They're specific against the capsid, and they go after it. So that was something that was noted early on. And then in the neuromuscular gene therapy trials, it had happened again in two flavors. One flavor was the flavor in myotubular myopathy, which is a congenital myopathy that's not unlike recessive RYR1 with the ophthalmoplegia, you remember this morning. And so, but this is a disease that not only affects muscle, but also affects the liver to some degree as part of the disease. So here you had a liver that already had a disease going on that was then triggered by the load of the virus to the liver, and then tragically 4 boys in that gene therapy trial were lost because the liver went into failure and couldn't be rescued. So that was really tragic because the effect on the muscle was so convincing. And so at the moment that's being retooled to find something that is less hepatotoxic. But both in SMA but also in Duchenne muscular dystrophy, the same thing has started to happen that we know from the early hemophilia trials, that the liver gets attacked by the cytotoxic T cells and reacting against the capsid of the virus. And that is, of course, something that is unavoidable. If you give the virus into the veins to get to every muscle of the body, it has to pass through the liver. So the liver gets a mega dose of the virus that just ends up there. We don't need it for neuromuscular gene therapy in the liver, but it is there and it's being exposed to the immune system. For most of the patients, that was a transient phase. So the liver inflammation showed up. You saw the liver enzymes go up, and then we could give some steroids, immune suppression, and then it would go away and the liver healed. But tragically, in a few cases, in few cases of spinal muscular atrophy, but also more recently Duchenne muscular dystrophy, and then also limb-girdle muscular dystrophy, that progressed. And it didn't heal out. The liver progressed into a phase that was no longer reversible, which was signified in the laboratory by not only transaminases, so the liver enzymes going up, but also now bile acids going up, and patients turned yellow, and the liver had a point of no return and tragically died. So that is something that needs to be further analyzed. It could be that this happened in Duchenne and limb-girdle situation in patients who were older, non-ambulant, and probably had a different liver composition because of years of steroids, of course, being non-ambulant, and probably somewhat more vulnerable liver, plus a very high dose of systemic gene therapy that goes on top of that. In SMA, it can actually also be that there may be a slight component of liver disease as part of SMA, the disease, which causes the vulnerability. Long story short, there one has to find that the liver is not avoidable in viral gene therapy. You have to pass through it. But what we have to understand is how we can mitigate that risk better. I think we are understanding well enough to take that on as a toxicity that's not precluding gene therapy, but that has to be addressed in gene therapy. So ways to take that on is, one is you could dampen the immune system so that it's not as actively making cytotoxic T cells against the viral capsid, and there's ways to do that, rational ways to do that. Secondly, you can decrease the dose of the virus that is needed to transact the muscle. So we probably talked about myocapsids here. So new capsids that not only go better to the muscle, but also detarget from the liver. So go less to the liver and more to the muscle. There where you can save a lot of load to the liver. And then also better understanding how to pre-screen and pre-treat patients to make the liver less vulnerable. There will be some reaction of the liver is unavoidable, but you want to have it reversed, just kind of pop up and then go back and not progress into this irreversible state. So it is tragic, it is disappointing, but it is analyzable, understandable, and addressable by science. That's my message to you.
So, and then just the last part of that, do you think, we just heard 3 talks, all involving viral gene therapy, 2 with AAV, 1 with HSV. Do you think, the FDA seems to be taking a hard line with Sarepta. Do you think these recent deaths is it just a transient sort of pause, or do you think this is going to set back the field of gene therapy for neuromuscular disease in a significant way?
I think it's a transient phase because there's several mitigation things you can do at this very stage. And so one is to identify more the risk profile and then maybe pull away from dosing patients with a high risk profile and go to patients where the safety profile is just better. I think there's no way around changing capsids in neuromuscular gene therapy. I think we have to get away from the legacy capsids, and so I think we have to face, and follow the science here to generate better and less dose needing capsids to do that. There is AAV gene therapy here forever? Probably not, but it's the best really that we have thus far, and it's furthest along, and it would be, I think, not a wise move to kind of shut down AAV gene therapy at this point when we have all the tools at hand that make it better. Could there be a new phase of gene therapy with non-viral delivery, new viruses? Yes, of course, but not in the very immediate future. And so I think we have to build what we have better and while we work at the future therapies.
Great. I saw Fruz jump up. Fruz?
I have a comment and a question for Carson. So the first thing is, among about 2,000 patients that received the AAV gene therapy for Duchenne muscular dystrophy, there was about 2 young boys and 1 recently about 50-something years old person. So do you think this number, so from 2,000 something who received only 3 deaths, so how much does it affect the entire gene therapy? And the second thing is, do you think we will see the same effect in RYR1? Because I believe in DMD, the case is completely different because they're losing the muscle. So there is less muscles for AAV to go in. And because of that, it may go more into the liver, right? But for RYR1 patient, we don't have that much muscle lose. So what do you think?
Good questions all around. So, so if you just go by frequencies, yes, it is a rare event. Also in SMA, it's a rare event when it occurs. In Duchenne, I think it depends on the population you look at. So if you look at the older, non-ambulant population where this happened, then the frequency looks less favorable. And so, but that also is a lesson to try to identify the risk profiles better and kind of avoid that dosing. The liver is always the first pass. So I think in RYR1 you can't count on your hope that it wouldn't kind of get stuck in the liver unless you have capsids that are detargeted from the liver. And that is also capsid engineering that's coming. There's Luc Vandenberg at Harvard designed a capsid where you can switch a toggle, literally, and let the virus not go to the liver, or at least much less, and pass through. And so that is kind of rational engineering of the capsids for safety and efficacy, where we're just at the beginning of a new evolution of that. And I think that'll get us into the right space. And lastly, also, we shouldn't underestimate that we have to even a gene therapy that's meant for all patients with a certain muscle disease, we still have to individualize it for the risks. And there could be individual susceptibilities of patients. So maybe a difference in the immune system, a difference in the liver, different in the complement pathway. Then we have to understand and tailor-make our therapies for that. My pitch always to all sponsors, they get sick and tired of me, but is that every patient at this day and age who receives a systemic gene therapy with AAV should have a whole genome sequenced and deposited so that we can go back and understand individual susceptibilities, differences in how our patients receive the gene therapy. And once we understand that, to kind of tailor-make our treatments to these patients to decrease the risks.
Great, thank you. All right, I want to talk about baby KJ. Has everyone heard of baby KJ? Hands? No one? All right, my mother knows baby KJ. All right, so baby KJ was born, I'm not sure if he was born at CHOP, but ended up at Children's Hospital Philadelphia with a rare genetic disease of the liver that I think has a 50% mortality rate. And researchers at CHOP, working with industry, developed a gene editing treatment that was administered to the baby at 8 months of age. So they diagnosed this baby basically at birth and tested the baby, developed a gene editing strategy, tested it in a mouse model of the liver disease. I believe they tested it in a non-human primate, and then ultimately gave this gene editing treatment, which was successful at 8 months of age. And after that happened, I had several emails to me asking, could this be done for RYR1? And so I would want to start with Dr. Hamilton and Dr. Dirksen at more of a basic science level. What are your thoughts about, developing, you work with mouse models of RYR1. If, one of our researchers developed a gene editing or one of the gene therapy strategies to go from a novel therapy, testing it in a mouse, and then I'll conclude with Dr. Bonneman, through a clinical trial to FDA approval. Is that at all in the realm of possibility for RYR1? I'll start with Dr. Hamilton.
Well, Mike, I think you know that I don't work on gene therapy, so I'm far from an expert on this. I do know one additional problem that we haven't discussed is that in all gene editing, getting rid of the editing machinery so that you don't have off-target effects. And I think that's something that all of us will have to consider, and Carson may want to comment on that. I hope we will get around to talking about therapeutics for those of you who are suffering right now with symptoms that you would like to alleviate and potential therapies for that. But I
as
can't
someone,
say much.
I guess what I was getting at, you are an expert. You have developed mouse models. You've worked with mouse models. You've tested therapies on mice. How practical, what's a reasonable timeline for testing a therapy, whether it be a small molecule we're talking about, and be able to assess the efficacy? Does it actually make the mouse stronger? That was kind of what I was getting at.
Sorry, I thought you were talking about gene therapy with the baby. The timeline, first of all, my laboratory created we've created a number of mouse models. Two of them I think are particularly relevant to this discussion. Both were dominant gain of function. One was the MHS susceptible that later developed central core disease. And the other was the gain of function, which instead of increased leak, actually had decreased release. So we've spent a lot of time characterizing those, and it's taken years to fully characterize those mice and to develop therapeutic interventions. In one case, where the release was decreased with the dominant, I guess you could call it a loss of function, we found that proteins weren't folding properly, and a chemical chaperone could improve muscle function in a mouse. Now, I'm going to say this over and over. A mouse is not a human. The mouse work is a starting point.
Yep.
It's an important starting point. But the mouse that we created with the poor blocking mutation is one of the most serious in humans. The mice are just barely affected. They're really mildly affected. So, if I can improve in the mouse, will that work in a human? I don't know that. The nice thing about that was the compound we used, the chemical chaperone, was an FDA approved. You can buy it over the counter, and it did improve muscle function in those mice. In the YS mice, we've actually found a number of things. In fact, I think therapeutically, the malignant hypothermia treatments for malignant hypothermia, in addition to dantrolene and Reichhaus, there are going to be a number of options there that should really, I think, improve life for those of you with MH. Maybe I should give Bob a chance to talk.
So Dr. Dirksen, Susan, Dr. Hamill, that was fantastic. Dr. Dirksen, you are actually working with some of the speakers that we just heard. And for everyone who doesn't know, Dr. Dirksen is the chairman of our SAB, Scientific Advisory Board, and is just a great advocate for this community, for R1 research, and has been very proactive working with Fruz and Celine and Hitchum, and it's just been a great collaboration. But so, Dr. Dirksen, what is a reason, given the premise of the question about baby KJ going from diagnosis to treatment in 8 months, what is a reasonable timeline from your perspective in assessing the efficacy and safety of a novel therapy in a mouse model, and be able to assess that and then maybe progressing it to the next phase? What do you think is a reasonable approach here?
Well, we have learned a little bit from studies that have been done previously to test various agents. So, for example, for PBA, also the NAC, which led to the NAC trial. Both of those kind of set of studies that were done by Susan, I was involved in some of them, they took 3 to 4 years really to kind of complete that kind of work. And those were with FDA-approved drugs that will not be a problem. With the incredible speed at which the KJ thing, I think that's setting unrealistic expectations for the muscle field. It's really a fantastic finding and cure for that baby. But they were able to take advantage of the fact that this was a liver disease and detargeting liver was not needed. So for muscle, we need to detarget and we need to effectively target. And then if you're talking about CRISPR, as Susan said, you have to kind of worry about preventing off-target editing. So those are going to take quite a bit of time. Just as Susan has, we've developed in collaboration with our own foundation models of severe recessive ROR1 myopathy, which those animal models are much more severe than dominant, as we see in humans. They're set up for preclinical testing of various agents. I would think it would take a few years to take one through that process. I'm very excited in the recessive models about delivery of full-length ROR1 as a therapy, ultimately for severe recessive. Why? Because ROR1 expression is very low, for number one. Number two, the proteins that are expressed typically have a variant that is dysfunctional. Maybe it's leaky, maybe it's kind of lacks release, like Susan was saying with the POR mutations. So if you express wild type, number one, you express more channels, which is great, because that's one of the fundamental problems, but you also break up these homotetramers of mutant channels into channels that have wild type, or I should say normal subunits, together with the variants, and that kind of dilutes the functional defects created by the variants and makes that individual more like their parent, which is typically asymptomatic and a carrier. So that's what you'd ideally want to do. So I think that these approaches that were discussed in the prior session, whether it's an AAV approach or whether it's a Intian-based approach using multiple AAVs or herpes virus that can have the entire payload in one virus. We still have the problems of detargeting liver. We still have the problems of delivering specifically to muscle. We can't be expressing this in the brain. We can't be expressing it in the heart. There are a lot of issues there. You can't really move to humans until you demonstrate this safety and efficacy in a valid mouse model, which the foundation has generated and has shared with all of these investigators. And I'm very excited about delivery of full-length protein as a rescue and as a long-term prospect for treatment in the recessive disorders.
Thanks, Bob. Carsten, from your perspective, Carsten, as Dr. Bonneman has participated in some of these trials, is the baby KJ model unrealistic for ROR1?
Well, so it really goes to the heart of the promise of genetic precision medicine and what that means. And I think it's of course a spectacular example of what can happen is, of course, several steps away for being applicable to RYR1 or even muscle disease, but it is absolutely not unrealistic to think about it, and I'll tell you why. So we often now find when we do our genetic testing, we found variants, we look at them and say, oh goodness, this is actionable. We can design a small molecule, an ASO, or even an editing technique to fix this. And a good example is Payam. He was in the clinic and we saw a patient with limb-girdle muscular dystrophy. Payam find a homozygous deep splice mutation, and he looks at it and says, I can fix this. And 2 weeks later, he comes back and had fixed it. He had an ASO that in the dish, in the lab, completely rediverts splicing to normal. So, that was in no time from just seeing the variant, developing a rational therapy, putting it into the dish and making it happen. But we didn't have a pathway from there to the patient, so that's lacking. But we now look at every genetic result with this actionable in mind. And you can, in the future, you can probably automate this, where the readout of variants comes with a list of actionable genetic approaches to that variant. That's one of the kind of pilots I want to do, is kind of every genetic report is actionable with a precision medicine mindset. Now then the next step, of course, is to develop the precision medicine tools to do that, be it ASOs or be it editing tools. That actually sounds complicated, but is probably not that intractable. You can probably find that for many variants, you find a strategy to do it. What comes next is, of course, much more complex, which is to develop a platform that allows you to plug it in with speed into patient translation. That is something that we have to work on and can work on. Once we have developed platforms that deliver to muscle and have a toxicology knowledge base behind them, then it becomes less and less necessary to do extensive toxicology in particular animal models or so on. For every individual genetic therapy, you have to do what's called genotoxicology. You have to make sure that it doesn't do editings or things that are unintended. So that has to be always done, but it can be done quickly and in cellular systems with next generation sequencing. And once we've kind of crossed that threshold that we've shown, we have delivery systems, we have kind of editing or small molecule systems that have proven a class effect safety, then we can pick up speed and move with a higher speed towards approval for single patients. What I've, of course, not touched upon is the cost of that.
Right.
And I'll leave that out of the room. But I think that the technicalities to get there are surmountable. I mean, they can be broken down in steps, and they can be established at platforms and then cross-fertilize the approaches. So I think it's up. And that's not specific to... The beauty of these approaches is they're really, in a way, disease agnostic. They're platform approaches. You need to know how to get to your target organ. You need to know what your genetic tool is that you want to do, but it's less important that it is RYR1 or Titin or another big gene. Right. So that's really where the mass effect comes from.
Dr. Hamilton?
So, Karsten, what kind of timeline? I think this audience is really interested in, will it help them?
I don't know. I mean, if we stop funding science, the timeline is out there. So I can only tell you in science and in approaches like this, the breakthrough can come out of left field and unexpected, and establish something that propels the entire field rapidly forward. And therefore, we have to continue to move in all these fronts at the same time, and that requires funding for science.
Yeah. All right.
One thing there's another story that's really amazing in the field, and that's the treatment of CF. And so there's the CF Foundation, very similar to this foundation, funded...
Cystic fibrosis.
Yes, I'm sorry, Cystic Fibrosis Foundation, funded research, basic research, to try to find a drug to treat cystic fibrosis. And what came out of that was a collaboration with Vertex and the discovery of 3 drugs that work to basically change the lives of children with CF that had a relatively short lifespan of less than 2 decades, and now they're living into their 50s on this drug called Trikafta. And it was based on a very simple, fundamental discovery in a lab, and that is that if you took cells from a CF patient in a tissue culture dish, and you put them at a lower temperature than physiologic temperature, the protein that didn't normally fold right and got degraded, and they didn't have the CF protein, would fold properly at 20 degrees or 25 degrees. And then it created functional CFTR protein in those cells. And now, that's not a treatment, but it was an assay now to look for drugs that would promote that, to do the same thing that temperature did. And they found 2 classes of drugs, 2 that are called correctors that help the folding, and 1 that's a potentiator that when the channel is at the membrane, it makes it work better. And they call this Trikafta. And it has changed the lives of children with CF. And maybe there is going to be that kind of discovery in RYR1, and maybe even in the RYR1 recessive field. We need to be looking for those type of discoveries that we can, save these channels that are not being made and bring them to the SR to work again. So, I mean, a lot of times you don't know what the next pivotal discovery is going to be, but we can learn from other cases where this has happened.
All right, we're a little bit over time, but any questions from the audience? Go ahead.
Have you ever tested temperatures in RYR1?
Yes.
We're doing it right now.
I get that one.
Dr. Hamilton.
So the image-susceptible mice are incredibly temperature sensitive. They can easily be triggered to undergo what looks like heat stroke by taking them to 37 degrees centigrade. So they get muscle cramps. If you look at the EMs of the mice, if they've been warmed slightly, they get what we call contracture cores. So you can see the muscle actually has contracted in places, not evenly across the muscle. So they're very temperature sensitive. And even very small changes in body temperature before heat exposure has a dramatic effect on heat exposure. I'm going to be talking about this a little bit more in the session. Is that what you were asking, or something different?
That's helpful to understand a little bit more.
I was also going to add, I thought where you were coming from is from the CF area, which we are actually testing this idea right now because we can make what we call myotubes. They're like early developmental cells in culture. And we know in those myotubes, RYR1 expression is very low in the recessive models, so we can make those cells very low. So my postdoc right now is culturing cells at 20 degrees, and we're also using drugs that we think will stabilize the protein in its resting state, like dantrolene, and seeing if these things will act as chaperones to increase expression. So we're in the process of doing this. It was very exciting. It may fail, but we're trying to learn from lessons from other fields and to see if this works. So if that's what you were asking, that's exactly what we're doing this week.
So one last, real quick, so for Dr. Bonneman, just want to, because we're short on time, but I just have to ask this question. I get this question from time to time from patients. Have people heard of what's called the N of 1 trial? Does that mean anything to anyone? N of 1?
What is it?
N of 1. So N means the number of people that are in the trial. So normally when you think about a clinical trial, you're talking about tens to maybe hundreds of people. N of 1 means there's one person in the trial. And so the way this might work in the rare disease community is you have a patient with a certain variant, certain mutation. Let's say a mouse model's developed with that variant. They test a therapy on that mouse. It seems to work. It seems to be safe. And then they go to a trial with one person, N of 1, sort of personalized medicine to the extreme. And I'm just wondering, Dr. Bonneman, your thoughts on that, its relevance. I know I'm aware of one that was done for Duchenne's that ended with the patient death. So Is that something, if a patient were to come to me and say, hey, because this has occurred, I want to fund this mouse, I think this treatment could work, and then I want to be eligible for that. Is that even something to be considered? Is it inappropriate? Is it unethical? Is it not? What are your thoughts on that?
So what one has to understand is that N of 1 is not a single clinical trial. N of 1 is part of a meta trial of personalized medicine. That's how you have to understand it. So by very nature, if you have an individual mutation that you address with an individual therapy and there's only one patient, that'll make an N of 1. But you have to do it as part of a meta trial of an N of 1 approach to disease. What I mean by that, the trial has to be done with the same ethical, scientific, and regulatory rigor than you would do an N of 500 trial, meaning it has to be a protocol that's submitted, a data collection that is absolutely sound, a supervisory committee that looks at the trial. It's not extended medical care that someone goes and buys a boutique medicine. It is part of the meta trial of developing personalized precision medicine, where every single trial will inform the next trials to come if all data is collected appropriately and shared appropriately as well, that the entire field can learn from that. If that's not the case, the ethical prerogative to start an NOI trial is not met. So it has to be done as a clinical trial with the same rigor and with the same intent to advance science for everyone else.
Thank you very much. All right, round of applause for our panel, Dr. Bonneman, Dr. Gerson, Dr. Hamilton. Thank you. It is really the all-star crew here. It's just amazing to see these people on the stage. I mean, I've been reading their articles for years, and to be on the same stage with them is truly an honor, so thank you.